My name is Ashley.
And my name's Chrissy.
And this evening in the 7 to 7:50 time block, we'll be covering MAC 1140, specifically going over rational expressions and everything having to do with rational expressions. This is a live and call-in show, and we'd like to hear if you have any questions or comments. Please feel free to give us a call. The number is 352-392-6420. You can also email your questions in tonight or throughout the week if you're watching this at a later date as a podcast. And you email your questions into uf-tutor@ufl.edu. If we get your questions tonight, we will stop whatever we're doing and answer them. If we get them throughout the week, we'll answer them the next time we do MAC 1140, which is on Monday nights. Tutor Time is brought to you by the Broward Teaching Center. It's here that we offer a variety of tutoring services to students for free. All you need is your Gator 1 card. We offer walk-in appointments, private tutoring. We have the TV tutoring, supplemental instruction for some courses. Again, all you need is your Gator 1 ID. And the schedule and the list of courses that those services are available for is on the Teaching Center website, which is teachingcenter.ufl.edu. And it's there that you can find everything you need to know out about the Teaching Center. There's also a map of how to get down to us. We're located across from the tennis courts behind Broward Hall in the basement portion. If you are watching this, or if you would like to watch this at a later date, you can't stay for the whole program but would like to see it, we do offer Tutor Time as a podcast. And it'll be up 24 hours from the time that the show airs. And you just go onto the Teaching Center website, and you can download it and take tutoring with you wherever you want. And then if you have a question while you're watching it, you just email it in. So it's very interactive. We'd love to have your questions, so please give us a call. So without further ado, we can jump into rational expressions.
Yes! I love rational expressions. So rational expressions are basically just the quotient of two polynomials. What's quotient mean? Quotient really is the answer to a division problem. So basically it means you're going to have a fraction with a polynomial on the top and a polynomial on the bottom. And recall that 1 can be a polynomial. Because what is a polynomial? Well, as we covered previously in the lectures, that's just an expression of the form an to the times x to the n plus an minus 1 times x to the n minus 1 plus ... all the way to a0, where a0 is just a constant here. So remember that you can't have negative numbers as part of the exponent. So all these n's are non-negative integers, and typically we write them in decreasing order. And then all of your constants have to be real numbers. So they can be integers, fractions, decimals, anything you want. But so the reason that 1 is a polynomial, well, it is of this form. It's just that we have 1 is equal to a0 here. So remember, if you have, for instance, a polynomial on the top and 1 on the bottom, that's still a rational expression.
All right.
Okay, great.
I think we might actually be getting a question. Or maybe not. We thought we had a question.
Okay, I think we can erase that part. Okay, so now that we have the definition down.
Thank you for calling. He said, thanks for the show. You did a good job.
Oh,
awesome.
Thank you.
Thanks.
Thank you, viewer. We appreciate you. And if you have any questions about anything, just call us back or email us. So now what we want to do is look at some rational expressions and find their domain. So let's go over what is domain.
All right, so domain, a kind of simple way to put it, is any value that we can plug in for the x. Now, sometimes our domains have restrictions, and when we're dealing with rational expressions, usually that restriction comes within the denominator, because, as we all know, the denominator cannot equal 0. So if we have just our basic form of our rational expression, our p over q, we know that q cannot equal 0. And so we're going to find out what values will make our denominator 0 and know that we have to exclude those values from our domain.
Mm-hmm. Yes, that's part of the definition of rational expression. So like she said, problem areas. Well, obviously when our denominator is 0, so when we have a rational expression on the bottom, the goal there is to set the denominator equal to 0, solve, and those values are not going to be part of our domain. Another problem area is when we have square roots. For instance,
or any kind of even radical.
Yes, square roots, right. Because remember, for instance, x to the 1/2 is just the square root of x. And we can write a little 2 out here. And x to the 1/3 is the cubed root of x. This has to be a positive number here because we can't take the square root of a negative number. However, with cubed roots, they can be positive or negative or 0. As you will see, for instance, if we did -1 times -1 times -1, well, that's just -1 to the third, which is -1. And that's okay for these numbers to be negative as well as that number to be
Right,
negative.
so the cube root of -1
Yep.
is just -1.
So,
And also know that for even radicals, those can also equal 0 as well. So that's why we have them set, the inside must be greater than or equal to 0.
so like she said, it's going to be anything that's even. So if we have x to the 1/2 or x to the 1/4 or x to the 1/6 and so on, those are going to be problem areas. And then one more thing that's a huge problem area is when we combine the two things. So for instance, when we have something on the top, doesn't really matter what it is, but we have something on the bottom that involves a square root. Well, we know the denominator can't equal 0, and we know a square root must be positive. So in that case, this thing becomes just strictly greater than 0.
Right, or if we have what are called composite functions, and then we have to look at, the domain of the first function, the domain of the second
Right.
function, and then mash them up,
And
kind
I
of.
think we get into that a little bit later in the course, composite functions. So, okay, let's look at some example problems. So let's just do a typical polynomial. So 3x to the 1,000th power plus 937x to the 74th plus 1.2298x to the first. What's our domain of that going to be?
All right, so it's a fun little rule for polynomials that our domain is all real numbers. So for any polynomial, our domain is all real numbers because of what Chrissy said, that our the exponents of our variables have to be integers. So all real numbers, that's for something like this. Again, the problem comes, or not the problem, but maybe the trickier part comes when we put a polynomial over another polynomial. But when we just have it by itself, we can have any number because think about it. I'm not limited by putting any number in these values. I can put
plug in
negative, positive, 0, anything, and I can get a value, y.
So what if I had this over x minus 3?
All right. Well, now we've got a little situation because now we have a denominator. So we have to take into account setting that denominator equal to 0 first, and then solving for what value that is for x. So in our case, we have x equals 3. So we know that our domain has to exclude that value.
So if we want to write this in interval notation, that's going to be -infinity to 3 parenthesis union 3 to positive infinity.
Right, and this interval notation is just excluding the value of 3. And that's why we use parentheses on both sides, because we know that it can't be equal to 3. We're excluding it.
And keep in mind that whenever you have negative or positive infinity, we always use the parentheses, not the brackets, because that's not an actual number. You never really reach it.
It's just a symbol
Yes.
to represent that our numbers go on for forever.
Okay, great. And be sure that you're able to write this because this is how it'll show up on your exams, the interval. So what if I had something like square root x minus 3 on the bottom?
All right, so now, like Chrissy said before, if we have a square root, we have to set the inside of the square root to be greater than or equal to 0. But the difference for us is that because it's in the denominator, it can only be greater than 0 because we can't have it equal 0 because it's in the denominator. So now we just set it to be greater than 0. We solve, so x has to be greater than 3.
So the domain here is going to be 3 to positive infinity. And if you're ever worried that you made a mistake or that doesn't sound quite right, then just pick something that's not in the domain and make sure that you can't do this problem. So for instance, if I pick x equals 2, well, let's try that. When I plug in the top, I'm just going to get a really big number. And on the bottom here, so this is going to go on maybe to infinity, then we're going to have square root of 2 minus 3. Well, I know that square root of 2 minus 3 is equal to square root of -1. And I know that causes a problem. So not part of the domain.
Right. So it's always a good way, if you think maybe that you're not so good at doing finding the domain, just pick, like Chrissy said, a number and test it. So
And also, if you're not sure if it should be a parentheses or bracket, go ahead and just test that number. So we take 3, we plug it in, we see we get the square root of 0. Well, that's fine. We can take the square root of 0. That's 0. But we can't have 0 in our denominator because we can't divide by 0.
right.
I would explain why, but we're just doing pre-calc. I think that's enough examples on domain. Is there? Oh, let's
Sid one.
do like
Bravo.
let's do another example. Let's say we have 7x plus 36 over x squared minus 4. How would we do that?
All right. So again, we're going to set our denominator equal to 0. So we have x squared minus 4 is equal to 0. We add 4 to both sides, and we get that x squared is equal to positive 4. So now we think, okay, we're going to take the square root. But here is a little trick. We have to take not just the square root. We have to take plus or minus the square root of x squared and the square plus or minus the square root of 4.
And another way to do this is if we set this equal to 0, we know this factors into x plus 2 and x minus 2. So that's what tells us that we're going to get a negative and a positive.
Exactly. So we get that x cannot equal positive 2 and x cannot equal negative 2 either.
So
I have an example too if you want.
let me just write this in interval notation. So we're going from negative infinity to negative 2. Union, and don't forget, we don't go automatically jump to the positive 2. We have to have everything in between these values. And then union again with 2 to positive infinity. And that's really important, is that you include this part in here.
And remember, again, just to go back and check, we can pick a number in each of these intervals, and it should work. And then we can also plug in negative 2 and 2, and it shouldn't work.
And just to review, the top is all reals. It's anything can be in that domain because it's a polynomial.
All right, I have an example that I saw a lot of people come into walk-in hours and kind of get a little hung up by. We'll just do minus. Okay, so we have this problem, and we need to, again, solve for the domain. So what a lot of people do is they want to simplify it first as much as possible, because that makes things easier, right? And so we would factor out both an x on the top and the bottom. So we would get x times 36 x squared minus 7x plus 8, and we factor out an x on the bottom. We get x, and we get x minus 1.
No! Like screaming in horror.
And then what they do is they cancel out the x, which is kind of, it's okay. And then we're just left with our denominator of x minus 1 that they set equal to 0, and they get that x cannot equal 1, and that's the only number that they exclude. But the problem here lies that we have to always deal with the original when looking at
domain.
So this is true. We can't have x equal 1, but we also have to consider this x here, and we have to set that x equal to 0. And so we have that x cannot equal 1 or 0. And so people think, well, I got to cancel it out. It's not going to be a problem. Like I can use my simplified version and plug in an x or plug in a 0, and I don't have a problem. But we always have to deal with the original. So what happens is when we cancel these out in our graph of this function, this is actually at x equals 0, we have a hole in our graph. So if you can simplify something from the top and bottom, you get a hole. So it's not an asymptote like this x equals 1 would be, but it still is not included in our domain. We still cannot plug in 0 because of our original equation.
So just further on down the course, if you wanted to write this, they're not equal unless you say such that x cannot be equal to 0.
Exactly.
Then that explains.
So if you factor out something, you can cancel it, but you have to remember that it has to, you still have to think about it when it's in your domain. If it's in your denominator, you still have to set it equal to 0.
So basically for domains, don't factor anything. Just work with your denominators because typically your numerators are going to be polynomials.
Or solve for your domain first by looking at the denominator.
Yes.
Don't factor anything. And then when you go to graph it, you can simplify and factor
Right.
that out. But you want to always deal with the original in any kind of situation that you're trying to solve for the domain. But that was a big, a lot of people had that kind of hang up when they came into walk-in hours this week doing their homework and their web assigns.
Okay, so let's go over some properties of multiplying and dividing rational expressions. So just to
Do you need
review,
this
yeah, we
delayed
can
anymore?
delete, erase. Let's review what we do with simply fractions. So if I have a over b times c over d, what do?
All right, so we, what I do is I multiply to the side. So I multiply a times c and b times d. So we get ac over bd.
However, my favorite is going to be dividing fractions. So when we have a over b divided by d over c, we use this thing called KCF, not to be confused with Kentucky Fried Chicken.
Keep,
So-
change, flip.
Yep, keep, change, and flip will be your best friend.
So sometimes it looks like this, but oftentimes they'll give us where it's a over b
All
over d over c.
Oh, shoot, I should have written this as just
You
because
want-
that's typically how it shows.
C
It
over
doesn't
D.
matter, but yeah.
Yeah.
Okay, so how do we do this? Well, we're going to keep our first fraction here. We're not going to do anything to it, so we just have a over b.
So we keep the top, and if it's given to you like this, you keep the top.
So then we're going to change our sign from division to multiplication. And then finally, with our last fraction, we're just going to flip it. We're going to take
Which
the
is the
reciprocal.
most fun part of this.
Yes.
Is the flipping always.
So this time we get AD over BC.
Right.
And that's really important. So if you don't know how to do this with fractions, review, because now we're going to be taking it one step further and doing this with rational expressions. as
Right.
we'll
So
see
with
now.
whole polynomials.
All right, if you want to, I'll tell you some examples we can do. So what we're going to do is we're actually going to simplify these rational expressions, and then we also want to find the domain. So what are we doing when we're finding the domain? Are we going to look at that first or after?
We're going to look at it first. Deal with
Absolutely.
the original equation. We're not simplifying anything first.
Okay, so let's look at x to the third minus 4x over x squared minus x minus 2. So I'll just do the domain on the side before Ashley simplifies this. And that means we're going to be looking at the bottom because the top is a polynomial, so we know any value will work for that. And so we set this equal to 0, and we get by factoring x minus 2 times x plus 1. So we know that x here is going to equal 2 and x equals negative 1, but be careful, that's what can't be part of our domain.
So you put some sweet
So we
slashes.
actually want to put slashes in it because we don't want any of these things equaling 0. So that becomes, our domain will be written in the form negative infinity to negative 1, union negative 1 to 2, union 2 to infinity. And remember, when you have two things here, that means that two values that can't be part of the domain, that means you're going to have three groups of being union together.
All right, so now let's get into kind of solving it. So like Chris said, we're going to simplify. And so we simplify the top. I think, okay, well, I can pull out an x from both of those. So I do that first, and I'm left with x squared minus 4. And I see, oh, okay, well, I can simplify that too, because that is what we call a difference of two squares, because x squared is a perfect square and 4 is a perfect square. So that's actually equal to x times x plus 2 and x minus 2. So that's on our top. And then our bottom, Chrissy has lovingly already factored it for us. So we have x minus 2, x plus 1 here, and then again, x minus 2, x plus 1. So since, what?
Sorry, you don't need that star.
Yeah. So since we've already done our domain, it's okay to simplify. So now I can think, okay, well, I can get rid of this x minus 2 from both the top and the bottom. And I'm left with x times x plus 2 over x plus 1.
So now you can see that if you hadn't done the domain first and you did it last, well, you'd say, well, duh, x can't be equal to negative 1 here. But that's not our whole domain.
And again, remember, you want to, because some people will say, oh, well, I canceled out 2, so I know that it can't be my equation. Look, I can even plug it into here. And they plug it in, and they do get a value, but that doesn't work because that's a whole. Yeah. So we have to go back to the original to get our domain. And so this is a simplified version of this function and probably what you're going to want to use when you go to graph it.
Okay, great. I think we have another one.
All right.
Oh, and I guess just to call what you're doing, the cancellation property says that A times C over A times B is just equal to A over A times C over B, which is just equal to 1 times C over B, and anything times 1 is itself. So that's where we get this. And that's just called your cancellation property.
Right, but we have to, again, remember that A cannot equal 0.
Oh, yeah, absolutely. I was just saying with fractions.
Exactly.
Okay. So we have some more examples
Alrighty.
with multiplying and dividing.
Okay. Let's divide something.
Okay, great, because that's what I had in mind.
Okay.
And the best way to practice this is always practice with division because it involves multiplication, so you get practice with both of those. And it's the harder one of the two. So let's look at x squared plus 4x plus 4 over x minus 7 divided by 3x squared plus 6x plus 8 all over negative 2x plus 14.
All right. So again, I know this looks kind of crazy, and I always try and make my my middle division between my top fraction and my
Longer.
bottom fraction much bigger, so I know that I'm dividing these two. So again, using the KCF property, we keep our top, we change our sign.
Well, before you do that, sorry. Just to start, there's 2 different methods for doing this. So I would recommend that you try both of the methods in your homework, find out which one you're more comfortable with or which one you feel like you're faster at. So one way is to simplify the top into one rational expression and then simplify the bottom and then do your division. Or some people like to do the division first and then do the simplification with factoring and everything. So I like to do it the second way, or where you flip everything first.
Yeah, I do too. But should we take into consideration, do we have
First,
to
we need
set
to
this
find our
equal to
domain.
0?
Well, this one didn't ask us to find the domain, so we don't have to do it.
Then we
no.
don't have to worry about it. So I go ahead, like Chris said, I use the second one first. I like to multiply much easier than I want to try and, because sometimes people get confused and they try and simplify this part.
Yeah.
And it just gets kind of crazy.
You have to be very organized with
So
this kind
I
of
go
work.
ahead and I
So let's just write an
keep
equal
change for-
sign. Yeah.
equals, it's a big equals. We have x squared plus 4x plus 4 over x minus 7. So I kept the top. Now I changed my sign to a multiplication sign.
And we'll use the dots so that we don't get confused with our x's.
Right. And I'm going to flip the bottom. So it becomes negative 2x plus 14 over 3x squared plus 6x
Plus 8.
plus 8. All right. So now I'm going to kind of break this down a little bit and see if I can simplify any of these portions.
The best way to factor.
Right. So this I know I can't factor x minus 7. I can't bring out anything or break it into 2 parts at all. Here, though, we can factor. And this becomes x plus 2 squared. Or we can write it as x plus 2 times x plus 2, which is how I would write it. Here, now I see I can bring out both a 2 from each of these portions, and I'm actually going to bring out a negative 2 because I want to get this coefficient of x to be 1. So if I bring out a negative 2, I get x minus 7. Oh, and looky there, I can cancel. That'll be real nice.
So let's leave them for now so we don't get confused with that.
Right. And so now we have this function, and
That factors into, so we have 3x and then plus,
they have to be pluses on both.
yeah, so plus 2 and then, or wait,
It doesn't, does it? Because it would have to be 4 and 2, or like 2 and 4.
Maybe I missed a minus sign somewhere. Maybe it doesn't factor, never mind.
We'll just leave it how it is. We won't factor it because, again, we can't factor this because
Yeah.
it would be 2 and 4 for this factor or 1 and 8. And 2 and 4 does add up to 6, but because we have this
signs.
3 here, it's not going to work. So we'll just forget that part. All right, and so now I can go ahead and cross, what we call cross multiplier. I can cross simplify, I guess, is what it really is. And cross simplifying there. And so now I'm just left with this x plus 2 squared
Times 2, negative 2.
times negative 2, and then this is simplifies to 1, over 3x squared plus 6x plus 8.
So that's your answer.
All right, and that's your answer. Now, if we had to go and find our domain, remember, though, we don't use this. We go back to our original.
And that means that the whole bottom fraction can't be.
Right, so we have to set each of
Actually,
these equal
yeah.
to 0.
Right. So what you would want to do first is not actually cancel anything, but just do your keep, change, flip.
Right, so we'd get the,
And actually, no.
it's
Yeah,
this one
it's
and
that
this one.
Mhm.
Right, so we would do our keep, change, flip first. And so we get our x squared plus 4x
So if
plus 4
Yeah.
over x minus 7 times, and then we have the negative 2x plus 14 over 3x squared plus 6x plus 8. So we know that both this one can't be 0 and this can't be 0. So we'd have to set each of those equal to it and find values, which wouldn't be very fun considering we know that this doesn't factor very nicely. But again, we couldn't, we don't want to just simplify this out. I keep saying it because it's very important, and I know a lot of people end up doing it and getting their domains wrong, which can affect a lot of things.
Okay, let's do another example.
Okay.
All right. So we want to simplify this as well. So we're going to have y to the third over 5y minus 7y plus 2. And let's use the division sign this time, just as to show a different way.
It's just 5y minus 7y,
Mm-hmm.
not squared.
No.
Okay.
Oh, yeah, sorry, 5y squared. Sorry. Divided by, and then we have y to the 6 over y squared minus 2y plus 1.
All right.
So this time, again, we're going to use our keep, change, flip. So we're going to keep our first fraction, which is y to the third over 5y squared minus 7y plus 2 times, now we're going to flip the second fraction, so the top becomes the bottom and the bottom becomes the top. So this time we get y squared minus 2y all plus 1. So again, if we were looking at the domain, then, and I should erase this as what the domain is, we could look at these two things right here, because that's technically our denominator. So we'd set this one equal to 0, and we get 0, and we'd also set this equal to 0. So let's go ahead and simplify, and we get, well, this is just going to be y to the third. And since I have a y to the 6 down here, I'm going to write this as y to the third times y to the third, because remember, when we're multiplying things with the same base, we can add their exponents.
No, you're not multiplying those two things.
I am multiplying.
You're dividing y third by y to the 6.
I know, but I'm writing this. Oh, sorry. Oops.
Yeah.
I meant on the bottom. So this is y to the third times, I meant down here, I'm going to write this as y to the third times y to the third. There we go.
Yeah.
Okay. So this one's going to factor into y minus 1 times y minus 1. And this one's going to factor into, let's see if it factors.
It does.
It does, yeah, actually. So we get,
Minus 1.
and then plus 2.
Minus 2.
Minus 2. Oops. There we go. So now because all of these things are multiplied, I can go ahead and cancel out one of these, one of these, one of these, and one of these. And so I'm left with, on the top, y minus 1 all over y to the third times 5y minus 2. And if we want to simplify, that's y minus 1 over 5y to the fourth minus 2y third. either way is acceptable and should be recognized on a test. So again, remember our domain is going to be, we can set y to the 6 equal to 0, which we know is just going to be y equals 0. And we can also set 5y squared minus 7y plus 2 equal to 0. And that factored into 5y minus 2 times y minus 1. So that means that y equals 1 or 2/5. So then the way to write our domain here would be negative infinity.
And we
to
also,
0.
are you just talking about for this one? Because we also have the y to the 6.
Yeah, I just did that one.
Oh, sorry, I didn't see
Okay.
that.
Mhm. And then we have 0 to 1. And then union.
2/5 is smaller.
Oh,
than
yeah,
one.
sorry. To 2/5.
Yeah, sometimes you got to make sure that they're right in the proper order from
Union.
smallest to largest.
2/5 to 1. Union 1 to positive infinity. So let's check. We have 1, 2, 3 different things. So that means we should have 4 different things there being unions. 1, 2, 3, and 4.
Right, and this is just set when it's set equal to. Sometimes when we have inequalities, it's a little different, but that's a good rule to use when it's just equal to and we're solving for 0. All right?
Okay, cool. We can move on then.
Yeah, again, if you guys have any questions about anything that we're going over,
Yeah, I mean, if you have a homework problem you're stuck on, don't wait till tomorrow morning to come see us. Just go ahead and call us right now, and we can do it for you live.
yep, or a web assign problem too, we
Anything.
can help with those as well.
Okay, so let's talk about adding and subtracting rational expressions. So let's look at a property. If we have a over b, oh, sorry, go ahead and write that. So the whole goal with rational expressions and addition and subtraction is going to be to find your least common denominator and sometimes the least common multiples. So what we do is, let's look at a over b plus or minus c over b. Once we have a common
C over D?
b,
Oh, okay.
once we have a common denominator, we can go ahead and add or subtract depending on what the sign is. So that means we have a plus or minus c all over b. And what's really important is not just to recognize this, which most people can, is be able to recognize it the other way. So this is an if and only if statement. So if we have a plus or minus c all over b, then we can break that up into two fractions, which sometimes it is necessary to go the other way. And since it's if and only if, we'll just write equal. And, okay. So what we're going to want to do to get common denominators is to look at the LCDs and the LCM. So let's do an example with that.
Okay.
And also to point out, this is only good if b doesn't equal 0, because we know that can't be in the denominator.
Mm-hmm.
All right, so let's look at some rational expressions. So let's look at 2/3 x to the negative 2, y to the negative 1, plus 5/6 x to the negative 1, y to the negative 3.
Okay, so the first step that you want to do is you want to bring any negative exponents to the
Yes.
denominator. So
We want to write them as fractions this time.
right, so I'm going to move this up here so I have a little more room. So now we have 2 over 3. The x squared goes to the bottom, and the y also goes to the bottom, plus 5 over 6 x y cubed. So that's our first step. So now we need to think, we need to somehow make these the same, and we need to multiply our terms by whatever it's missing to make our denominators the same.
So that's going to be our goal, is to get a denominator of that, because that's going to be the smallest multiple possible. So in order to get 6 on the left side, we're going to have to multiply by 2 over 2. And again, remember, whatever you do to the top, you must do to the bottom.
Right, so I just write it as I'm doing it to the bottom, and then I repeat the same thing on the top. So
fine.
I need a 2 because I need a 6.
And we also need
I've
2
got
y's.
the x squared, but I need to add 2 more y's to my y. And so then I just repeat it on top. And then over here, I have the 6, and I just need an x now both to make this complete. So I multiply by x over x. And up top here, I get 4y squared over, again, the same denominator that we we're reaching 6x squared y cubed plus 5x over 6x squared y cubed. And like Chrissy said, because of this principle, we can just keep our denominator the same to be the 6x squared y cubed. And we just add the top. So the top becomes 4y squared plus 5x. And that's our completed combination.
Yep. And now we could simplify if we wanted to. We can divide by 2 on the top and the bottom.
But we wouldn't want to necessarily divide by 2 on the top and the bottom because we have a 5 here. And that
Oh, the
doesn't,
5, sorry. Well, we
yeah.
can simplify the x's and the y's then. And you can still simplify that.
How would you want to simplify that?
So if we have, this is really saying 4y squared, or I'm just going to write 20 because I have a 4 times a 5. So we have 20y squared times x times, now we have 6 to the negative 1, or I'm just going to write it like this. 6x squared y to the third. Now remember that if we have y squared over y to the third, that's equal to y squared minus 3 up here, which is equal to y to the negative 1, or 1 over y.
Mm-hmm.
So this part is going to be, let's look at the 20 over 6. Well, I can divide both of them by 2, so I'm going to get 10 on the top and 3 on the bottom. And here we knew that this one is just going to be y, and on the top I have an x.
Chrissy,
over
those are
x
added
squared.
together. They're not multiplied.
Oh, you were adding? Oh,
Yeah,
sorry, I
that's
looked
what
at the
you-
bottom.
That's what you were giving
What
me.
happened to the signs?
No. Okay, so we had this
Oh,
plus this.
okay. Sorry.
Yeah, so there's no way to simplify it.
I was
which is
looking
why
down
I
at
was
the
really
book.
confused. There's no way to simplify it. This is as simple as we can get. Because remember, we can't pull out anything from the top and
So
anything
you
from the bottom.
have, okay, my bad,
Right.
my bad.
So it's a combine just like this is. Because this is the type of problem that
Sorry,
we're
I
doing.
didn't see your plus sign there. That's why I was like, hello.
Yeah. Well, that's why I was like, what
Oh,
are
yeah.
you doing?
I just glanced at it and didn't see her.
But again, because we only multiplied each portion, each term by exactly what we needed to get the denominator.
Right,
so we
right.
couldn't really have simplified it all.
Sorry, just keep that in mind for when you're doing multiplication.
Right.
Okay, then we have another example.
All right.
You can erase the subtracting and adding property if you want, so you have more
Okay.
room. Okay. Let's do 1 over x plus 1 minus 2 over the quantity x plus 1 squared all over, or I'm sorry, plus, my bad, plus 3 over x squared minus 1.
All right. So what I'm going to do is I'm going to break out the denominators into their most factored forms to see what I'm going to need for my least common denominator. So I just have this x plus 1. I can't really do anything with that. Minus 2 over x plus 1 times x plus 1 plus 3 over x plus 1 times x minus 1. So I see that I have at least 2 x plus 1s here. So my least common denominator has to include at least 2 x plus 1s. And I have 1 here, so that's fine. And it also has to include an x minus 1. So that's my least common denominator. So I have to multiply each term by what I don't have. So on this first term, I don't have one of the x plus 1s, and I don't have the x minus 1. So I need to multiply both the top and the bottom by x plus 1, x minus 1, and then we have times 1 over x plus 1 times x minus 1, because we just want this to be a ratio of 1 over 1 over this x plus 1. All right, and the 2, in the second term, we are only missing the x minus 1, so we have minus x minus 1 over x minus 1 times what we have originally, which is 2 over x plus 1 times x plus 1. And then this last term, we just need one more x plus 1. So plus 3, we're going to multiply that by x plus 1 over x plus 1 times x plus 1. I'll move this over so it doesn't get confused. So what this results in now is that we have, I always run out of room. I write too big. X plus 1, I'm just going to write it squared, times x minus 1 all over x plus 1 squared times x minus 1 minus, we don't want to change our signs, 2 times x minus 1 over x plus 1 squared times x minus 1. And then we have plus 3 times x plus 1 over x plus 1 squared minus, times x minus 1. All right. So now that we have that, we can just combine it all into one simple fraction, because this will work down to, it's all over our common denominator because they all have the same thing, x plus 1 squared times x minus 1. And we have x plus 1 squared times x minus 1 minus 2 times x minus 1 plus 3 times x plus 1. We could go through and multiply it all out, but not really necessary for what we're doing. So this is what it would work to combine each of these with a least common denominator.
Yep. Okay, great. More examples. Do you want to keep writing?
Let's switch.
Okay. So I was going to ask you.
All right.
All right, so we're on this one.
Which one?
That one.
All right, so we're working with complex fractions.
Yeah, I'm going to release this. Okay, what do we have?
Complex fractions are quotients containing rational expressions.
Right.
So, yeah. All right, so
The definitions are your notes.
Yeah, we're going to simplify this expression. We've got 2 minus 3 over y all over 4 minus 9 over y squared.
Okay. Can I use the other marker?
Oh,
Okay, you're good. All right, so this one is actually what I think I was referring to earlier about the methods, where there really is two ways to do this. So you could do your keep, change, flip first, and then work from there, or you can try and simplify this into one expression on the bottom. So I'll go ahead and simplify the numerator, the denominator, and then flip it, but you could also do it the other way.
I feel like most people do it that way, where they simplify, they get a common denominator on the top.
It just depends
the
your
bottom.
preference. So maybe we'll do the next problem the other way just to show. So this one, my common denominator here is going to be y, and here it's going to want to be y squared. So to get that, I'm going to have 2 times y over y minus 3 over y all over 4 times y squared over y squared. This a little bit bigger. Minus 9 over y squared. And then I can go ahead and combine these since I have a common denominator. So that's going to be 2y minus 3 over y all over 4y squared minus 9 over y squared. And now I'm going to go ahead and do my keep, change, flip. So don't forget that. We keep the first fraction, 2y minus 3 over y. We multiply instead of divide. And now we flip the second fraction. So on the bottom I have 4y squared minus 9. And now what we want to do is simplify that. So here in multiplying, what I'm going to do is actually look at the factors here. So here I get a 2y minus 3. All right, well, I can't really factor that. And here I get a y times y. And on the bottom, I have y times, and this can be broken up since it's the difference of two squares, into 2y minus 3 times 2y plus 3. And since these are all combined by multiplication, that means I can go ahead and use my canceling property. So I have 2y minus 3 and a 2y minus 3, and then a y and a y. So this becomes y all over 2y plus 3, our final answer. So you can see that you might start with something that looks complicated and it looks like it involves a lot of steps, but as long as you're very organized and methodical, you can just get to the simple answer. So, and I do want to clarify something. If we have 2y plus 3 over y, I can break that into 2y over y plus 3 over y, which is equal to 2 plus 3 over y. However, if I have what I have here, y over 2y plus 3, this is not equal to y over 2y plus y over 3. I don't know where people got this from, but it's not right.
Yeah, people like to simplify things, so they think that they can simplify up and down. But when what you have to realize is that when things are on the denominator, they're kind of in a family. So unless you can separate one child out of the family, we can't
Yes.
simplify it. So
That's a good way to think
2y
of it.
plus 3 is a family. We can put parentheses around it, and we can't bring anything
Right.
out of there to be able to simplify it. So that's why we can't just simplify it as y over 2y plus y over 3.
So make sure you understand the difference of these two, and don't ever do this, please, please, please. And remember that when your teacher says simplify, sometimes you might not get something so simple. You might have something a little more complicated, but that doesn't mean that your answer is wrong. There is a point where you have to stop. You don't want to keep going unnecessarily, because then
Right,
will
you
be
have to look and see if you can pull anything out of the top and then pull the same thing out of the bottom. That's
Right.
simplifying. But if you can't really, then
stop.
yeah, then stop. You're
It's
fine.
okay to not spend 30 minutes on a problem.
Do you want to do one more
Yeah,
problem?
I can do one more real quick.
All
What's the
right.
next one?
So we've got one more example for that. And again, it's simplifying complex fractions. So you've got x squared over the square root of x squared plus 1 minus the square root of x squared plus 1 all over x squared.
Okay, so I'm going to want to go ahead and simplify our top into one rational expression. So that means my common denominator here. So our goal is to get a common denominator of x squared plus 1. And remember that when you have no denominator here, that's not really true. You do have a denominator. It's just everything's always over 1. So this is going to be x squared over x squared plus 1 like we have it. And then this one I'm going to multiply by x here. All over x squared. And so now I can combine this into x squared minus, I'll write the x first, x times square root of x squared plus 1 all over square root x squared plus 1 all over x squared. And now I want to use my keep change flip. So that'll give me x squared minus x times square root of x squared plus 1 all over square root of x squared plus 1. And remember, this fraction here is x squared over 1, so this becomes 1 times x squared. Don't mix that up, as people often do. And here, since I can pull out an x, I'm going to get x minus square root x squared plus 1 all over square root x squared plus 1 times x squared. So finally, my answer, since I can cross out an x from both sides, is going to be x minus square root x squared plus 1 all over x squared plus 1 square root times x.
Right, and you'll learn a little later that we'll have to simplify that even more, but
Yeah.
For right now,
We'll
it's
leave it.
fine. All right, so that is it
Great.
for today for rational expressions. Again, if you have any questions throughout the week, send us an email at uf-tutor@ufl.edu. And you can also catch the show on Monday, or you can go down and download the podcast.
And since the next show is actually 11:40 and it's so closely related, you're welcome to call your questions into that show as well.
Exactly. So, again, have a great night. Good luck with your homework, and hopefully we'll see you on Monday. Oh, wait. Do we have tutoring on Monday?